in our showdown, we've got an 867 megahertz G4 against the 1.7 gigahertz Pentium 4. And in the showdown, in the showdown, the G4 completed the task in 45 seconds. The Pentium 4 took 82 seconds for the same exact task. That means the G4 at this task is 80% faster than a 1.7 gigahertz Pentium. Now, I know what you're thinking. How can this be? How can this be? And the answer to this question is a technical one, but the name that we've given it is the Megahertz Myth. And to explain the Megahertz Myth for us, I've asked John Rubinstein, our Senior Vice President of Hardware at Apple, to come up and give us a brief tutorial on the Megahertz Myth. John? Thank you. All yours.
Thank you, Steve. Morning, everybody. Okay, so you just saw the G4 beat the Pentium 4. And some of you are thinking to yourselves, wait a minute, 1.8 gigahertz, that's twice as fast as 867 megahertz. And those of you that are thinking this are suffering from belief in the Megahertz myth. And that is that megahertz equals performance. But megahertz does not equal performance. It's just a contributing factor to performance. Now, to understand this, we have to look at how processors are designed. There's a lot of complicated trade-offs in processor design. And I've picked 4 of the key architectural trade-offs for us to look at. Of course, there's frequency. We want to run as fast as possible. The frequency will be based on what process we're in and the number of pipeline stages. The more pipeline stages we have, the less work we do every cycle. And so the faster the pipeline can run. These two are very much related. And there's some real downsides to having long pipelines. We're going to talk about that in a minute. Then there's a number of functional units. The more functional units you have, the more parallelism you can have. That's how many instructions you can execute every cycle. And the cache design. Whether you have a level 1, or the size of the level 1, size of the level 2, and if you have one, the level 3 cache. So all of these factors play into what the performance of the processor is, not just frequency. So let's look at some examples of this. Here are the 4 leading processors in the industry today. The PowerPC G4, my personal favorite, the Pentium 4, Intel's next generation 64-bit architecture, the Itanium, and Sun's latest Spark processor, the UltraSpark 3. We can compare several characteristics of these processors. We can look at the process, the size, the number of pipeline stages, and how many megahertz they run at. Now, it's interesting. Most people would assume that because the Pentium 4 runs at 1.8 gigahertz, that it would be in a much faster process. But the reality is all 4 of these processors are in the same process, give or take. And it's interesting to note that the G4 is a very efficient design, because it's half the size of the other processors. Now let's look at how Intel got to 1.8 gigahertz. They did that to going to 20 pipeline stages. Now we see that the G4 is only 7 pipeline stages. So you're thinking, well, what's a pipeline stage? So all processors execute instructions through their pipeline. This is a very simplified version of it. It's a 4-stage pipeline. Instruction gets fetched, decoded, executes, and the results stored. Now all the processors we're looking at have more pipeline stages than this, and they have 1 or more of these pipeline stages broken down into multiple pipeline stages. Let's look at an example of this. We have the 7-stage G4 versus the 20-stage Pentium 4 here, and we're going to execute equivalent instruction streams down these pipelines. So we see instructions flowing down the pipeline, and the short pipeline starts getting results sooner. It takes us a while to fill the longer pipeline. Now we start seeing some results coming off the long pipeline. So right off the bat, the long pipeline has a disadvantage in that it takes longer time to fill. Now every cycle we're executing 1 instruction and completing it. So you're probably thinking, well, wait a minute, the longer pipeline is running twice as fast as the shorter pipeline. And so at some point in time, it's going to catch up to the short pipeline and pass it. And that would be true in the ideal case. But it's not a perfect world. And there's inefficiencies associated with long pipelines. That's been called in the press lately the pipeline tax. And the pipeline tax occurs because there are bubbles in the pipeline that come from data dependencies. That's where one instruction is dependent on the data from a previous instruction. Or even more catastrophic is certain branches can cause the entire pipeline to drain. So let's take a look at this again. Now again, we're going to run the same instruction stream down both of these pipelines. We see that the short instruction pipeline starts generating the results first, and you start to see some bubbles. So you see bubbles. Now bubbles can be one to many clock cycles. Now we see a branch. That's the red instruction. You notice the pipeline drains. Now the instructions get to the end of the long pipeline, and that one drains. So we see that whenever we hit one of these kind of branches, we pay an enormous penalty for having that long pipeline. Now the short pipeline drains. We see a variety of bubbles, more branches, and we see that the longer pipeline falls farther and farther behind the short pipeline. Okay, there's the last branch on the short pipeline. Finish that last instruction. Continue executing along. There's the final branch for the long pipeline. Now these branches, data dependencies, occur very often, right? And it really depends on what your code looks like. Okay, now we'll finish up that last instruction. And we're done on the long pipeline. So let's go back and compare our four processors again. Okay, we have the Pentium 4 running at 1.8 gigahertz and those 20 pipeline stages. It's interesting to look at the Itanium because, again, Intel's next generation processor, they chose to go with 10 pipeline stages. Note that it runs at 800 megahertz. And we see the UltraSpark 3 has 14 pipeline stages and runs at 900 megahertz. So the G4 is an extremely efficient design in that it only has 7 pipeline stages and yet runs at the same speed as other processors that have much longer pipelines. So I hope that this gets you to understand that performance is more than just megahertz. And I hope you're not fooled by the megahertz myth. Thank you, everybody.
Thank you, John. So, again, the megahertz myth. An 867 megahertz G4 can be as fast or even faster than a 1.7 gigahertz Pentium 4, and it gets even better when you add 2 G4s in the multiprocessor model. So these things are very, very fast.